My name is Joonas Multanen, and this is the presentation for our paper Programmable Dictionary Code Compression for Instruction Stream Energy Efficiency. First I will go over the background, then I'll introduce our proposed method, I'll go over some results, and conclude the presentation. First, a bit of background. The instruction stream in a processor can effectively be thought of as an overhead. It doesn't actually contribute to the computations. The instruction stream can constitute up to 40% of total system energy in some cases. A field of study of code compression aims to represent often occurring instructions with fewer bits compared to their original format. Our proposal is to use code compression as a method to improve energy efficiency in embedded systems. For this, we propose to use runtime programmable parallel dictionaries. As previous work has noted, overheads of dictionary compression are relatively low when compared to statistical methods such as Huffman. A common approach in previous works is to program the dictionaries or dictionary once at program start and be done with it. Runtime programmable dictionaries are more flexible, as you can change the contents as you will, and they may allow better compression ratios. It should be noted that all instructions do not benefit from compression. For example, instructions that are only executed once in the program. Compressing them would only incur additional overheads. In our approach, we selectively compress the most beneficial instructions or their subfields. This results in interleaving uncompressed and compressed instructions in the instruction image. To select the most beneficial instructions, we propose a selection heuristic. To keep execution overheads low, we want to access each instruction with one fetch only. And this leads to fixed size instruction bundles and boundaries. This is shown here, where you have a bundle of 3 compressed instructions, along with some padding bits, to match the width of the uncompressed instruction. The idea here is also to program before and not during program hotspots, such as loops, as this may cause significant overheads. For this, we use control flow graph analysis to form compression regions. Here is a more detailed overview of our method. We start with the source code, which we compile into assembly. For the purposes of this paper, we do basic block and control flow graph analysis from the assembly code. With the control flow graphs, we then select regions to compress, followed by creating dictionaries for each of the compression regions. We then insert control code, which in our case are special header instructions telling how much to fill to each dictionary. Finally, since we are dealing with code compression, we have to fix branch target addresses, after which we can finish the image. When the compressed image is loaded into the instruction memory, it looks like this. We have headers, which tell how many entries are followed by it to be programmed into dictionaries. After the entries, we are free to interleave uncompressed and compressed code, shown here. This is what a compressed bundle looks like. It is simply a number of instructions fixed at design time, and each instruction merely consists of indices to all of the dictionaries. And this is how the instruction fetch hardware looks like. We have a number of dictionaries in parallel, and for each of them we can configure their number of entries and the width. During execution, we can either fetch uncompressed or compressed instructions. We evaluated our method in an embedded system scenario using zero-risky, which is a RISC-V core. We compared with 2 different compressions. First, the RISC-V compressed instruction set, and the state-of-the-art method in the field of programmable dictionaries. And here is the evaluation setup. We first have an instruction memory scratchpad, optional instruction cache, connected to the zero-risky core, where we have an instruction fetch and decompressor. Here are results for the dynamic compression ratio. On average, the RISC-V compressed instruction set performed the worst resulting in around 18% reduction in the fetched number of bits. Our method was followed by it, around 30% reduction in fetched bits. Slightly better was the method by Tureson et al. However, if we take a look at the runtime overhead, we can see that the method by Tureson et al. Performs significantly worse. And this is due to them compressing all of the instructions in the program image. As we talked about before, this can lead to excessive overheads when inside loops. If you have a programming instruction inside a loop, you will always have that overhead in each iteration. Since we do the programming before program hotspots, we are able to reach on average around 1% overhead. Of course, the RISC-V compressed does not have this overhead, since it doesn't program any dictionaries. And the overhead you see here is due to compiler differences between the RISC-V compressed and normal. Results for energy consumption are presented here. Here we present numbers for the core, dictionary, cache, and instruction memory. As a baseline, we have the zero RISC-V with no cache, shown here on the left, followed by 3 different cache configurations, not using the compressed extension. As you can expect, the instruction cache lowers the energy consumption, except with the very small block size, where the cache is constantly missing and the energy consumption is increased. With the compressed extension and no cache, we can see that on average we can save around 10% of the system energy. When incorporating a cache, we can lower the energy consumption further. With our proposed method and no cache, we achieve around 15% reduction in system energy consumption, which is 5% better than the RISC-V compressed extension. We have proposed a programmable code compression scheme to minimize the dynamic compression ratio and improve system energy efficiency. Our proposal is to selectively compress instructions while keeping the overheads low, fetching each instruction with only one fetch. We also propose to program dictionaries outside of program hotspots with the help of our compiler analysis. In an embedded scenario, our method reduces system energy consumption by 15%. Compared to RISC-V compressed extension, the reduction in system energy consumption is 5% on average and 21% in the best case. Thank you for your attention.